Next thing I want to do today is some couple examples of what are called trigonometric substitutions. And in this first example, we're going to be motivated by trying to confirm that the area of the unit circle is pi. So here's the unit circle. Its area, we know, since the area of a circle is pi r squared, would be pi times 1 squared, which is pi. That would be equivalent to showing that the area of a quarter of the circle is pi over 4. Let's do that. Let's show the area of a quarter of a circle is pi over 4. How am I going to do this? Integrate the function representing a quarter of a circle right there from 0 to 1. But what function is that? That's y equals square root of 1 minus x squared. So the point I'm trying to make is, to confirm this, we need to integrate square root of 1 minus x squared. Let's do it as an indefinite interval first, and then to confirm the area here, we'll do a corresponding definite interval. Integrating something like this is not easy. If it were 1 over the square root of 1 minus x squared, that actually would be easy. What would it be if you integrated 1 divided by the square root of 1 minus x squared?
Arc sine.
Arc sine. Inverse sine. Same thing. It's a memorized one. But it's not 1 divided by the square root of 1 minus x squared. It's just square root of 1 minus x squared, which makes it harder, actually, even though in theory it's a simpler looking function. We're motivated by trigonometric identities, like the fact that sine squared equals 1 minus cos squared theta, sine squared x equals 1 minus cos squared x, and the fact that we have a 1 minus something squared there, to maybe replace that x with a sine function. It's traditional to call the variable theta. Let x equals sine theta, which is equivalent to theta being inverse sine x, or if you prefer, arc sine x. Calculators use the inverse sine. Mathematica actually uses arc sine. Just like usual, we've got to find dx in terms of the new variable. Dx d theta would be the derivative of sine theta, which is cos theta. That means dx is that derivative cos theta d theta. Right, since the derivative of sine is cosine. So now in this integral, I'm going to replace the x with sine theta, and the dx is going to get replaced with cos theta d theta, which makes the integral look harder, but it's actually easier. Looks can be deceiving. Now, technically speaking, okay, one way to see that it's easier is to replace that 1 minus cos squared theta equals with sine squared theta. Now, technically speaking, the square root of a square of a number is not the number. Did you know that? The square root of a number squared is not the number. This does not equal a. But wait a minute. Don't we use that sometimes? Doesn't this equal a typically? Not when a is negative, it doesn't. When a is positive, it does. But if a were like -5, -5 squared is positive 25, and by definition, the square root of positive 25 is positive 5, not -5. Oh, so you have to put absolute value signs around the number. That's how I get around it. So technically speaking, this is the absolute value of this. I made a mistake here, didn't I? Sorry, this should be sine. And this should be cosine. Technically speaking, this is the absolute value of the cosine function. However, we don't like dealing with absolute value signs. Let's just pretend it's positive. Assume cosine theta is positive, which means theta itself can be taken to be between negative pi over 2 and positive pi over 2, which is negative 90 degrees and positive 90 degrees. So that this equals cosine. Is that okay? Well, it's kind of a situation where the ends justifies the means. We get the right answer in the end. Actually, in the case where theta is not between negative pi over 2 and positive pi over 2, in the case where cosine theta is negative, we actually end up two negatives making a positive in the end anyway. That's why you end up getting the same answer either way. Hey, and that's cos squared theta, d theta. That was the integral we just did. 10 minutes ago, 15 minutes ago. This integral. Use that. I'm about to use it. 1/2 theta plus 1/2 sine theta cos theta. Put it over here more. 1/2 theta plus 1/2 sine theta cos theta plus c but remember, we need to get back to x. The original integral involves x. Any thetas can be replaced, though, by inverse sine x. And in fact, it's a little simpler with these. Since x is sine theta, I can replace this sine theta with an x. What about cos theta? Should I replace that with dx over d theta? You could, but it's not real helpful. Instead, use your trig identity. Cos theta is plus or minus square root of 1 minus sine squared theta. And here's where in the case where cosine theta is negative, that the two minus signs would cancel. In the case where you pick a negative quantity here, you'd also pick a negative here. I assumed cos theta was positive here, so I can actually take the positive there. Replace this with square root of 1 minus, replace the sign with x, 1 minus x squared. So the final answer is, for the integral, 1/2 theta gets replaced with inverse sine x. That's what this is, inverse sine x. And then I get a plus 1/2 x square root of 1 minus x squared plus c. That is the integral that we started with. Wow, right? You wouldn't have guessed that that would be the answer. That would be really hard to guess. Let's check it quick by differentiation. Differentiate our answer. 1/2 inverse sine x plus 1/2 x square root of 1 minus x squared. I'll want it right as 1 minus x squared to the 1/2 power plus c, which will differentiate to 0. The derivative of inverse sine is 1 over square root of 1 minus x squared, but I also have the 1/2 in front, which can be brought down as a 2. I need the product rule for this part, right? It's the product of two functions. The derivative of 1/2 x is 1/2. That's the derivative of the first times the second, plus the first function times the derivative of the second. Bring down the 1/2, subtract 1 from the exponent. Then don't forget the chain rule. To multiply times the derivative of 1 minus x squared is to multiply by negative 2x. And then the derivative of c is, of course, 0. This must simplify a lot. Yeah, it does. Get a common denominator of 2 square root of 1 minus x squared, which you already have here. So just leave the 1 as is. You don't have that denominator here. There's a 2, but not a square root in the denominator. So multiply this by square root of 1 minus x squared divided by square root of 1 minus x squared to get the right denominator. And when you multiply the top by square root of 1 minus x squared, you get this expression without a square root, because this is already a square root. Right? 1 minus x squared to the 1/2 is the same as square root of 1 minus x squared. If I multiply that by square root of 1 minus x squared, the square roots do cancel. It is true that square root of a squared does equal a, though to use this formula, you're really assuming a is greater than or equal to 0. You're not allowed to use it, in this class at least, when a is negative. Square roots of negative numbers are imaginary numbers. We will talk about imaginary numbers in here, but not right now. This part actually already has the correct denominator because you see a 2 there. And with a negative 1/2 power there, that's the same as 1 divided by the square root of 1 minus x squared. But then I can cancel one of the 2's. And I also have x times x. I get a minus x squared here. And in the end, the 2's divide out, and this simplifies to square root of 1 minus x squared. Take a number and divide by its square root. It's the same as a to the first power divided by a to the 1/2, which is a to the 1 minus 1/2, which is a to the 1/2 square root of a. When you divide a number by its square root, you get the square root of the number. And that's what I was hoping I would get, right? I'm differentiating the answer. I better get the function I was integrating, and that's what that was. There's the original problem. So again, here's the final answer. Kind of complicated. What was my goal here? I wanted to confirm the area of a circle is pi by confirming the area of a quarter circle is pi over 4. So I need to do a definite integral to confirm that. Definite integral from 0 to 1 of square root of 1 minus x squared. We already found the antiderivative is 1/2 inverse sine of x plus x square root of, I forgot my 1/2 again, 1/2 x square root of 1 minus x squared plus c evaluated from 0 to 1. There's what I get when I plug in 1, subtract what you get when you plug in 0, which even though it will be 0 here is worth writing out. You want to be careful. Sometimes it's not 0. That's a 0. This is a 0. This is a 0. You're left with 1/2 inverse sine of 1. Inverse sine of 1 is pi over 2. So the answer is pi over 4. Inverse sine of 1 being pi over 2. That really is something you should remember, though you can, of course, double check it. Make sure you are in radian mode, which I am. Inverse sine of 1 is pi over 2. So then I get pi over 4 at the answer here. confirming the area of the unit circle is pi. Nice to see math is consistent. But it took a fair amount of work. Can we use calculus to confirm other formulas from geometry, like the volume of a sphere, for example? Turns out we can, and we will. Not too long either. I think before spring break even. We'll confirm the volume of a sphere is 4/3 pi r cubed with calculus. Volumes, really? Aren't we doing areas so far? Yeah, but calculus can be expanded to deal with volumes as well. Next example is this one. Integrate square root not of 1 minus squared, but 1 plus x squared. Not 1 minus x squared, but 1 plus x squared. Here, if I try to use x equals sine theta, like in the previous problem, it's not very helpful. You still could try it, but it's not very helpful because if x is sine theta, then you'll get a 1 plus sine squared theta, not 1 minus. It will not simplify to cos squared theta, and you won't be able to take the square root so easily. So we need something different. We are motivated by another trigonometric identity that is related to this one. We know cos squared theta plus sine squared theta always equals 1. If you divide everything by cos squared theta, you'll get another trigonometric identity that is always true when it is defined. Divide everything by cos squared theta. Cos squared theta divided by cos squared theta is 1. Sine squared theta divided by cos squared theta is tan squared theta. And 1 divided by cos squared theta is what we call secant squared theta. The plus sign there, matching the plus sign here, now motivates us to let x equal tangent theta instead of sine theta. Let x equal tan theta. Like always, I guess I have to figure out what dx is in terms of the new variable. The derivative of tangent is secant squared. I might also need the fact that theta will be inverse tangent of x. That might be helpful as well. Make the substitution, replace x with tangent, get square root of tangent squared theta, replace the dx with secant squared theta, d theta. That's a secant squared theta, and I'm taking the square root. Technically, I get the integral now of the absolute value of secant theta times secant squared theta. But once again, if we assume we're in the situation where secant theta is positive, assume secant theta is positive, which would happen if theta is between negative pi over 2 and positive pi over 2. We'll get the right answer in the end, so we're not going to worry about it. But in order to finish the problem, I have to integrate secant cubed. Now, last Friday, we did the integral of secant squared, right? That was easy. That was tangent plus c. And we did the integral of secant, which was not so easy and required the fancy trick of multiplying by secant theta plus tangent theta divided by secant theta plus tangent theta. And the answer involved natural log, of all things. We've got a secant cube now. Is it easy or hard? The answer is it's hard. But we can make use of what we did last Friday. We can do it by parts. We want u and v to be v prime to be chosen so that the product is secant cubed. So probably one of them needs to be secant squared and one needs to be secant. Most important bit of advice is make v prime be something easy to integrate. So make that be the secant squared. So that v is tangent. And then let u be the other factor, which is secant. And therefore, u prime is secant theta tangent theta. The derivative of secant is secant times tangent. If we now use integration by parts, uv minus the integral of vu prime with respect to the variable, which is theta again. U times v is going to be secant times tangent minus the integral of v times u prime is going to be the integral of secant times tangent squared. Doesn't seem like we've helped ourselves much, but it is okay. We are making progress. We can replace this tangent squared theta with, based on this fact up here, solve this for tangent squared theta, you get secant squared theta minus 1. This can be replaced with secant squared theta minus 1. I'm just using the same identity, just subtract 1 from both sides. And that might seem worse, but it's actually better. Because now, once again, same thing happens as before. The right side involves the integral that I want to find being subtracted, and I'm going to be able to add it to both sides and solve for it. But it also does involve the integral that we did last Friday. That was complicated, the tricky one, integral of secant. But the answer we got last Friday is that this is natural log of the absolute value of secant theta plus tangent theta. That's what we got last Friday. Tracking with me here? Take a breath. We're not quite done yet. What was our goal here? Our goal is to integrate secant cubed. We've got the integral of secant cubed to be equal to all this. I need to now add the integral of secant cubed to both sides to get 2 times the integral of secant cubed on the left side. And everything else here on the right side, plus c. And then because of the 2, I need to divide everything by 2. Just like we did before. So what I'm trying to say is the integral that we want, integral of secant cubed, is 1/2 of everything on the right, essentially. 1/2, except for that thing which we added to both sides. 1/2 of this plus 1/2 of that. And then go ahead and lop on the c at the end. But we're still not done, right? What are we still missing? Got to go back to x. That's the original problem right there. Replace any tangent thetas with x. Replace any secant thetas, look at this one equation, with square root of 1 plus x squared. And yeah, you can take the positive square root, that's fine. Replace any tangent of x, tangent theta, with just x. Replace any secant thetas with square root of 1 plus x squared. And the final answer then is for the integral of square root of 1 plus x squared is 1/2 x times square root of 1 plus x squared plus 1/2 natural log of, I think I'll write it in the opposite order again, x plus square root of 1 plus x squared plus c. Pretty amazing that that can be done. But it is complicated.